Okay, so have you ever really stopped to think about that invisible force that's powering, well, literally everything around you? I mean, the screen you're looking at, the lights in your room, it's all thanks to electricity. But here's the thing, not all electricity is created equal.
And that's a great question, right? Because they feel so different. Power from a battery is kind of like a steady, predictable river, just flowing in one single direction. But the power coming out of your wall, whoa, that's a whole different beast. It's called alternating current, and it's basically the secret language of our entire electrical grid.
So on one side, you've got direct current, or DC. Just think of a battery. It's a simple, one-way street for electricity. And on the other side, you've got the power in our homes, alternating current, or AC. Its defining feature? It is constantly, and I mean constantly, changing its mind and reversing direction.
So you might be asking, why on earth did we choose this seemingly chaotic current to power everything? Well, it all comes down to one incredible superpower. AC's voltage can be easily cranked way up or way down using something called a transformer. This lets us send massive amounts of power over huge distances with very little energy getting lost. That's something that's just incredibly inefficient to do with DC.
But what does it actually look like for a current to alternate? To really get it, we need to see it in action. So let's break down the anatomy of an AC wave.
And there it is. This beautiful flowing curve is called a sine wave, and it is the visual heartbeat of AC. Just look at how it smoothly rises up to a positive peak, dips back down through zero, falls to a negative peak, and then comes right back to the start, completing one perfect cycle before doing it all over again. So, how do we measure this thing? Well, the first property is amplitude. The easiest way to think about it is just the height of the wave. It shows us the maximum voltage or current that the circuit hits in either the positive or the negative direction. The higher the amplitude, the higher the peak power. Simple as that.
All right, next up we have the time period. This is just how long it takes for the wave to complete one full cycle, say from one peak all the way to the next peak. It's the duration of that single repeating pattern.
And that leads us directly to frequency. So if the time period is how long one cycle takes, frequency is how many of those cycles are happening every single second. We measure this in hertz, and it's really the true measure of how fast that current is flipping back and forth.
And this isn't just theory, this has a huge real-world impact. Here in the US, our power grid operates at 60 hertz. That means the current is completing 60 full cycles every single second. In a lot of Europe and Asia, it's 50 hertz. This frequency is the invisible, standardized rhythm that our entire electrical world is dancing to. Okay, but this constant change creates a brand new puzzle for us. If the voltage is always swinging from, say, positive 170 volts all the way down to negative 170 volts and back again, how can we possibly give it a single practical value? How do you measure a target that's always moving? I mean, really think about it. That wave is perfectly symmetrical. It spends the exact same amount of time in the positive zone as it does in the negative zone. So what do you think happens if we try to take a simple average of that whole thing? The answer, and this is kind of wild, is zero. Yep, the positive half of the wave and the negative half are perfect mirror images. So over one full cycle, they completely cancel each other out. An average value of zero tells us absolutely nothing useful about the power that is very clearly lighting up the room. Right. Clearly, 0 volts isn't the right answer. My lights are on. So engineers needed a much smarter, more effective way to actually describe the power of an AC circuit. And the solution they came up with is called the RMS, or root mean square value. Now, don't get hung up on the name. The idea behind it is brilliant. It just asks a simple question. What amount of DC voltage would produce the exact same amount of heat as this AC wave? It's this really clever way to measure the effective power of AC by comparing it to its DC cousin. And here's the big aha moment. When you plug something into the wall here in the US and you see 120 volts printed on the label, you're not seeing the peak voltage. The actual peak is way up there, closer to 170 volts. What you're actually seeing is the RMS value. It's the effective, practical, and most useful number in the entire world of AC. So now that we've broken it all down, let's put these two types of current head-to-head for a final scorecard.
This table really just lays it all out. You can see that core contrast, right? AC is dynamic. It's reversing direction, its magnitude is always varying, which makes it perfect for the grid. DC is constant and steady, which is why it's the undisputed king of batteries and solar cells. They each have their own job to do.
So, what's the big takeaway here? Why should you even care about the difference between a flowing sine wave and a flat, straight line? It really boils down to three key things. First, AC's defining feature is that constant reversal. Second, that ability to change is what allows it to be transformed for efficient, long-distance travel. And third, when we need a practical, usable number for AC, we use its effective RMS value. Now, just let this sink in for a moment. In a 60 Hz system, the flow of electricity completes 60 full cycles every second. That means the direction of the current is literally flipping back and forth 120 times every single second. It's this frantic, invisible dance that's happening inside your walls right now. So the next time you flip a light switch, you'll know it's not just some simple flow of power. It's this incredibly complex, oscillating wave of energy. And it kind of makes you wonder, what other powerful, unseen forces are silently shaping the world all around you at this very moment?